If you've ever managed a Kubernetes cluster at scale, you know the scaling tax. You spend half of your time tuning auto-scaling groups, managing instant types, and staring at unschedulable pods while waiting 5 minutes for a node to join a cluster. Today we are talking about Karpenter. We're going to cover what it is, why it's fundamentally different from the old school cluster autoscaler, and how it actually works under the hood. Then we're going to touch on the installation and show how to elevate the entire experience using Cast AI to add that extra layer of autopilot optimization. By the end of this tutorial, you're going to see why the industry is moving away from static node groups and towards just-in-time infrastructure. Let's get started. So what is Karpenter? At its core, Karpenter is an open source, high-performance Kubernetes node provisioner. But to understand why it's a game changer, we have to look at what it replaces, the Kubernetes cluster autoscaler. Think of the old cluster autoscaler like a bus system where you have fixed routes. These are your autoscaling groups. And if the bus is full, the system is going to send another identical bus. It does not matter if you only have one passenger left. You are going to pay for the whole bus. So that's slow, it's rigid, and it's a nightmare to manage if you need diverse hardware like GPUs and ARM instances. Karpenter is the Uber or the Lyft of Kubernetes because it doesn't look at groups. It looks at the pods. So when a pod is unschedulable, Karpenter bypasses the autoscaling group abstraction entirely and talks directly to the EC2 Fleet API, and it says that, hey, I have a pod that needs 4 CPUs and 8 gigs of RAM and an NVIDIA T4 GPU. Give me the cheapest instance that is available in this availability zone that fits that criteria. We use it mainly for 3 reasons. Speed, because it can provision nodes in sub 1 minute by not waiting for the autoscaling group health checks. Cost, because it selects the best fit instance from over 750 EC2 types to ensure that you are not overpaying for unused capacity. And the last one being simplicity, because you can just delete dozens of managed node groups and replace them with a single Karpenter configuration. We're going to see this in action as well in the demo of this video, so make sure you stay tuned till the end. Karpenter pulls this off by operating as a controller inside your cluster that constantly watches the kube scheduler. When the scheduler flags a pod as unschedulable due to the resource constraints, Karpenter kicks in to perform a process called bin packing. It basically aggregates all the pending pods and calculates the most efficient packing onto a new node using 2 primary CRDs or custom resource definitions. First one being the node pools, which basically defines how Karpenter should provision the nodes, setting constraints like only use spot instances, limit to instance families, or only like you can expire nodes after 72 hours. And the second one being EC2 node classes, which basically handles AWS specific configurations like AMIs, security groups, subnets, and IAM roles. Once a node is running, Karpenter doesn't just set and forget. It is obsessed with efficiency and performs consolidation, meaning that it notices that 3 pods are, let's say on a massive M5 4x large, and they can actually fit on something smaller, something cheaper, like M5 large. So it will gracefully drain those pods and kill the big node and spin up the small one in a continuous real-time Tetris sort of a way for your infrastructure. Installation is straightforward but requires precision, as you typically install Karpenter via Helm, which requires setting up IAM roles for service accounts, so the controller has permission to create EC2 instances while ensuring that your cluster is configured to trust these new nodes as they join. But here is where it gets interesting. While Karpenter is brilliant at provisioning the nodes based on pod requests, it has a blind spot in that it trusts your developers. So if a developer requests 2 gigabytes of RAM for a microservice that only uses 200 megabytes, Karpenter with every single duty, so dutifully, it's going to buy you a node that is 10 times too large, which is exactly where Cast AI steps in to elevate that experience. Cast AI basically sits on top of Karpenter to solve the human error problem by providing automated right sizing, which basically looks at the actual consumption of your pods and shrinks the request to match the reality, so Karpenter makes even better, cheaper provisioning decisions. It also adds predictive spot orchestration, providing a layer of spot intelligence that predicts interruptions before they happen to move workloads to safer pools, and offers unified visibility through a single pane of glass to see exactly how much money Karpenter is saving you and where any remaining waste lies. So if you're combining Karpenter's raw provisioning power with Cast AI's workload intelligence, you move from automated scaling to autonomous optimization. Okay, let's now install Karpenter. Step 1, we're going to install the Karpenter controller. Think of it as the brain of the operation. It's a small pod that is going to sit in our cluster and constantly watch for any applications that are waiting for more CPU or more RAM. Step 2, the blueprint. We are basically going to give Karpenter its blueprint and its rules. So the node class tells it which AWS subnets to use, and the node pool is going to tell it to prefer on-demand instances to start. We are also going to enable consolidation, which basically means that if a node sits empty for 30 seconds, Karpenter is going to kill it immediately to save us money. All of these commands are very easy to get started with. You don't have to write down as I am writing on the terminal, because you can find these on the official Karpenter documentation that we will leave in the resources below. Now that the installation is complete, let's see if it's working correctly. We are first going to check the brain of Karpenter. So we are looking for pods in the cube system namespace. As you can see, they are showing up as running and have 0 restarts. So the controller is healthy and is watching our clusters. Next, we are going to verify that the Kubernetes API has been extended. We should see resources for node pools and the EC2 node classes. And these are the new languages that our cluster now speaks to manage the AWS hardware. Finally, we are going to check if our node pool is active. This is basically just a set of rules that we gave Karpenter, like preferring on-demand or spot instances. If this list was empty, it would mean that Karpenter doesn't know how to scale. Even if the pods are running, we can see that it says ready as true. So Karpenter is installed. As always, check out the official documentations. Links can be found in the description below. Now let me show you some of the features of Karpenter and let's see it working in action. Now that we have Karpenter installed, before I launch anything, I need to show you how Karpenter thinks. So in terminal 1, I'm going to open my watcher. Basically, this is the window that gives us a live view of our cluster's hardware. As we demand more power, you're going to see Karpenter provision new nodes here in seconds and not just minutes. In terminal 2, I'm going to show you the brain of Karpenter. It's a real-time log of every decision that it's making. It's currently scanning our clusters every few milliseconds, waiting for a pod that has nowhere to go. Now we're going to create a massive demand for resources that our cluster can't handle. We are going to ask for 10 CPUs and 10 gigs of RAM. In a standard cloud setup, these pods would sit in pending state for like 5 minutes while an auto-scaling group slowly warms up. But here, look at the logs. Let's check the status of our pods. Here you can see that some of the pods are failing because they have nothing to do. So I'm going to update them with a sleep command. And now you can watch as they transition from crash loop to a healthy running state. There you go, pending. And we can see that our log was made in Karpenter as well. Launched node claim. There you go. And here we can see a new node is up. In previous 3 seconds, it's not ready yet, but it should be ready in a few seconds. There we go, ready in 17 seconds. And you can see the logs in Karpenter as well. So it's working well, working good. So instead of a few minutes, things are happening in seconds. Let's check our pods now. We can see that all the pods are running and stable. On the far right, you can see the IP addresses of the brand new node Karpenter just built for us. And we have gone from 0 capacity to a fully operational environment in under 30 seconds. Let's delete the other deployment that we have. Karpenter is built for efficiency. Now that our stress test and the demo are over, I'm removing the workloads. And in a traditional cloud environment, these nodes would sit idle for 15 minutes, costing us money. But as we're going to see now, by watching Karpenter's logs, it's going to identify that these nodes are empty. Let's look at this new terminal. The nodes are being coroned, marked as unavailable, and then deleted from AWS. Karpenter just shut down the hardware in real time because we no longer have a business need for it. This is how you achieve a true scale to zero architecture. Now, here is the big money saver. I am updating our Spire worker pool to prefer AWS Spot instances. So we are basically telling the cluster to hunt for spare capacity that costs up to 90% less than standard nodes. So I'm now launching a demo Spot workload requiring 10 CPUs. Notice that I'm adding the sleep command to keep these pods active and healthy. Karpenter will spot the need and will provision the new nodes right now. And here we go. You can see that the new node is up, and in the Karpenter logs we can see that it's a Spot instance. So it's working. We are running a full-scale production workload on the cheapest compute available in the cloud. And this node was ready in like 20 to 30 seconds. So Karpenter is already great at scaling, but if you want to take it a step further, you can actually layer Cast AI on top of it. Think of it as giving your autoscaler a massive data-driven brain. Cast AI runs continuous analysis across tens of thousands of clusters, using machine learning to study how workloads actually behave and how the spot market is shifting in real time. So instead of just reacting, the system starts predicting. It identifies which spot pools are the most stable and flags potential interruptions before they even happen. It then takes that data and handles the heavy lifting, things like adjusting workload requests, picking better instant types, and rebalancing your nodes automatically. And because it's a learning system, it actually gets more accurate as your clusters evolve. Now the best part, you don't have to change your setup. You can keep Karpenter as your core autoscaler, and Cast AI just plugs in to provide the optimization signals and automation to make it run smarter. It's basically all the benefits of advanced machine learning without having to touch your core scaling logic. Onboarding is incredibly straightforward. Whether you use the UI or Terraform, once you connect your cluster, Cast AI automatically detects Karpenter and starts evaluating how it's performing. It digs into the details, workload patterns, node selection, and spot behavior to see where you are actually efficient and where you are leaving money on the table. From there, you get a clear roadmap of improvements. We're talking about right-sizing workloads based on real-time CPU and memory usage, finding more stable spot pools, and even using container-lib migration to keep your apps running during maintenance. You also get a full visibility into how these scaling decisions impact your bottom line and system reliability. And if you are ready to let the AI do the heavy lifting, you can just enable the automation. It's going to handle the resource adjustments, node replacements, and continuous rebalancing for you. You also get total visibility. You're not just seeing a bill, you're actually seeing exactly how much you saved through right sizing, spot usage, and consolidation. You can break those costs down by workload, namespaces, or teams, which makes life a lot easier for both engineering and FinOps teams. The workload optimizer is like a smart tuner for your applications that watches their actual CPU and memory usage and automatically adjusts their requests to match. Instead of guessing your resource needs and leaving a huge buffer for just in case, it right sizes your pods based on real-time data to eliminate waste. This keeps your applications performing reliably without the risk of throttling while significantly lowering your cloud bill. The impact dashboard is where all the optimization work becomes visible, showing you the exact ROI of your automation in one clear view. You can track your total monthly savings and see your percentage reduction in costs, alongside a real-time chart that proves how much waste has been cut from your CPU and memory requests. It breaks down the savings by specific workloads and namespaces, so you know exactly which services are running the leanest and where the biggest wins are coming from. The Node Autoscaler is the engine that handles the heavy lifting of your infrastructure by making sure you always have the perfect mix of compute for your workloads. Instead of sticking to the rigid preset instance types, it scans the entire cloud market in real time to provision the most cost-effective and high-performing nodes available. It automatically manages spot instances, handles graceful interruptions, and constantly rebalances your cluster to pack pods efficiently and eliminate idle capacity. It's essentially a set it and forget it way to ensure your underlying hardware is always optimized for both cost and reliability without any manual intervention. And that's how you turn Karpenter into a fully automated cost-cutting machine. All the links can be found in the description below, including the documentation and the features that we have covered in this video, so you can dive deeper into the technicals. If you're ready to see these savings on your own clusters, just head over to cast.ai to get started. It only takes a few minutes to connect your cluster and see your first optimization report. So definitely go check it out. Thanks a lot for watching. I will see you in the next one.